So in chapter 3 we're studying dynamics, and dynamics again, it explains why motion happens. So we saw kinematics describe the motion, so we sometimes say it describes how motion happens. In dynamics we express why motion happens. So taking the most trivial example, one of the ones that we first analyzed, which is free fall. I have a pen, I let it go, why does it fall? Why doesn't it stay there, right? And then it was the starting of the conversation that we saw in the lectures, and it's going to take us to this common sense theory saying forces acting, forces not acting change motion, and all the way down to buried down through Galileo, through Isaac Newton and his 3 laws. And all there is in this chapter actually is just understanding the concepts to be able to apply them more conceptually, because numerically it's pretty trivial. Everything numerically comes from Newton's second law, which is sometimes called the law of acceleration, and oftentimes also referred as to the fundamental law of mechanics, because every mechanics problem is pretty much in the classical way solved by adding all the forces together, finding the net force, and then saying force is equal to mass times acceleration. But let's just quickly remember the 3 laws, and it's very important that you understand the concept of these laws so you can start to analyze motions according to these laws, because then you're going to start to understand how nature works and avoid those intuitions and misguided intuitions, and we are misguided many times, as we saw, because for instance if I say why the object doesn't move is because I'm not pushing it, and then we just saw that actually that's not a correct answer. That's just simply because we live in a world that is with friction, and so objects come to a rest, but they come to a rest because there's a force acting against that motion. If there was no force, and that was the great insight of Galileo, if there was no force acting against them, if they could be in vacuum, objects would keep moving forever, and they would keep moving in a straight line forever with constant velocity. So there's nothing more natural about being at rest than there is moving with constant velocity. So the 3 Newton's law are going to be the law of inertia, right, which says that objects keep moving unless with constant velocity, unless there is a net force, right? So that's the first law. So unless there's a net force on the object, velocity is going to be constant. If velocity happens to be 0 now, it will be 0 later. But if velocity is 5 meters per second, it will be 5 meters per second later. So unless there's net force acting on the object, and net meaning again the sum of all the forces that are acting on an object, velocity is going to be constant. And velocity constant means that the direction is constant and means the magnitude is constant, so this is going to be moving in a straight line with the same increments in position for the same amount of time. Second law is the fundamental law, which is sort of the formula, which just tells us that force is equal mass times acceleration. So this is why we can say that this is the fundamental law of mechanics, because every time that we have an object and we have a distribution of forces, then we're immediately going to be able to find acceleration. And if we find an acceleration, this is a vector, of course, because this is a vectorial magnitude, then we can decompose in a sub x and a sub y, and then we just use kinematics. This is all the problems of this chapter are based on this idea. You put the net force, then divided by the mass of the object, you're going to get accelerations, put them, and solve for the kinematic equations, which is exactly the same thing you've done in chapter 2. So they're just adding a way of finding out the acceleration, but there's nothing new. And the third one is the law of action and reaction. And I like to phrase this one as saying, a way of remembering is what A does to B, B does to A. If you want to be more formal, that any force acting from object A imprinting a force on object B is the same as object B, or actually when A hits B, B hits A, but with the same force but opposite direction. So it's just going to be that the force of object A over object B is as the force of object B over A, but with a minus. It's opposite. Now it's important in action reaction, do not make this mistake when you're doing a free body diagram, which is, as we will see in a second, a few examples, forgetting about everything and just focusing on your object. Replace your object with a point, a mass point, or a point particle. Now we're going to be considering mass because we need to obtain the acceleration by dividing by the force. See all the forces that are acting on there. Those are vectors. Add the vectors together, and then you're going to have a net force. Divide by the mass, decompose in x and y components, and you're all set, right? But it's very important that you don't confuse action and reaction. So this is the force that A does on B. This is the force that B does on A. If I'm analyzing the motion, or let's say this is for object A, and it hits object B, right? This is the force that A does to B, if you want, and this is the force that B does to A. If I'm analyzing the motion of object A only, then object A is only going to be having one force. If I'm analyzing the motion for object B, I'm going to have the opposite, right? This is the only force. But force BA is not acting on object B, is the object B acting on A. That's not considered when I'm analyzing the motion of B. Okay, very important. You only consider forces acting on the object. So whatever way you define these subscripts, in the order you define them, don't make the mistake. And second one is that this is a very important principle. Because for instance, if you want to, even if there are more forces present, individually each one of those forces have its own reaction. Because there are forces in the classical way we saw that they are the result of two objects interacting with each other and changing their state of motion. And of course, if I have a nail and I hit it with a hammer, the nail was stationary and it starts to move, so it has changed the motion. It has changed acceleration. If there's an acceleration, it's because there's a force, and what is exercising that force is actually being exercised by the hammer hitting it. But I can analyze the motion from the point of view of the hammer, and what I see is I had a hammer with initial velocity and final velocity is 0. So it's also changing the velocity. And what's the acceleration? Therefore, because it's changing the velocity, I'm going to have an acceleration, and if there's an acceleration, it's because there's an interaction. What is acting on the hammer to stop it? Well, that's the nail. So that's why we say the action force is, let's say, if you wish, the action reaction here is not like a causality. They both act at the same time, right? So hammer is hitting the nail, changing the motion of the nail. Nail is hitting the hammer, changing the motion of the hammer. If I'm analyzing the hammer, I only consider the force of the nail on the hammer. If I'm analyzing the nail, I only consider the force of the hammer on the nail. But I don't account, when analyzing the motion for the nail, about the forces the nail might be doing anywhere else. That's irrelevant. Only forces acting on the object. That's very important. And the second thing is what A does to B, B does to A. Classic example, a problem that almost everyone always gets wrong. Imagine there's a chandelier, or let's just make a, this is supposed to be, okay, it's supposed to be something, a bucket, not the chandelier, we're not that fancy. And so we're saying, okay, this object has a force that we're going to call weight in chapter 4, we'll see it. So there has is being attracted by Earth. And I ask, what is the reaction of the force of gravity acting on this object? And it's very typical that people say, well, it's hanging from the roof, so then the reaction is the tension, because it's a string. But that's not the case. What A does to B, B does to A. If what is the to B in this case is the bucket, right? So who is doing anything on the bucket? Well, the Earth. So Earth to bucket. So what's the reaction of this force? Is B to A, Earth. So the reaction of the Earth pulling from the bucket is not the tension. The reaction is the bucket pulling from the Earth. So that's the reaction. And you see, of course, you don't put that force there. That's irrelevant if I'm analyzing the bucket. So again, the presence of other forces acting on the object should not confuse you about the action and reaction. Action is Earth pulling from the bucket. Reaction is bucket pulling from the Earth. And this, as weird as it sounds, is true. Objects fall to the Earth, but also the Earth falls to the object. So we say I drop an apple or I drop this pen and it just falls towards the Earth, but also what's happening is that the Earth is going up against my marker. Of course, because objects have different mass, you will see that the same force with different sign, you see that the force needs to be divided by the mass. So the acceleration of my pen, and then I'm going to have the same, and then I'm going to have the acceleration of the Earth, right? It's going to be the force, the same force, but now I'm going to have a huge mass. And so, of course, this acceleration is very little. So that's why it doesn't move. If I run against the wall, I'm changing my state of motion. I was running with certain velocity, and then I have 0 velocity, right? So I just smash the wall. What happens? Well, there's a force acting on me. What's the force? That's the wall pushing me. But action, reaction. What the wall does to me, I do to the wall in the opposite direction. So I'm also actually acting and applying a force against the wall. The truth is that the acceleration of the wall is going to be very little because the wall is very massive, whereas I'm not that massive. So acceleration is large, very large to me, but it's very small to the wall. So when you were a child and then you hit someone and say, hit me, like they punch me, right? You could say they faced me on my fist or something like that, and then you're allowed. So dynamics allows you to do that sort of assessment. So let's see some problems on how to use this. Let's remember the principle of inertia. Let's forget for once and for all that things change their motion. Remember, things change their motion whenever there's a net force, and that doesn't mean And that doesn't mean that the object was moving or not. Object can be doing whatever it's doing, whatever it was doing will keep doing in the absence of force. Second law tells us mathematically how to do that. We calculate, we net force, we divide by the mass, and extract the two components, and then use kinematics. Easy peasy. And let's not forget action and reaction, because this is going to allow us to understand many of the motions. So all these three laws are the three laws of dynamics. There are the three laws of Newton, and then we use them to solve all the problems. So let's see some problems. Problem 1, for instance, from discussions. Problem 1 says there is a tow rope that will break if tension exceeds 1500 newtons. So we will see more about tension and all this in chapter 4. For the time being, let's say there's a car over here and it's trying to be towed, and the force cannot be, so the force needs to be smaller or equal to 1500 newtons, right? The car is 700 kilograms. And so it says, what is the largest acceleration the rope can give to the car? Easy. Force is equal to mass times acceleration. Larger acceleration is going to be force divided by mass. How do I achieve the maximum acceleration? Whenever I apply the maximum force. If I apply 2000 newtons, what will happen? Well, if I apply 2000 newtons, the rope will break. So I cannot apply 2000 newtons. If I apply 500 newtons, what will happen? Well, the 500 newtons is smaller than the maximum, so that's going to be fine. It's going to produce an acceleration. But if I apply 1000, I'm going to get twice as much acceleration. In fact, the maximum acceleration is going to achieve whenever I have the maximum force. And so, of course, the maximum acceleration is just going to be the maximum force, which is 1500 divided by 700. And this cancel, and so I'm going to have 2.14 meters per square second. So again, that's maximum acceleration. So if I wanted to know, oh, maybe I need, let's say that instead of a car being towed, just think about other scenarios where this might be relevant. For instance, you have one of those chainsaws to cut the trees, right? And you have to start it, right? You have a starter, and the starter doesn't have with the modern cars that have like a starter motor. You're gonna do it manually, right? Pulling from the string. Well, that string might be that one. That string needs to produce enough acceleration to start the engine. If you don't produce enough acceleration, the engine doesn't start. So how do you choose the string to actually be able to start your chainsaw? Well, you're going to be making sure that whatever force, whatever acceleration you need, you could do the opposite, the string can sustain that sort of force. Simple examples. This is all there is in this chapter. Again, we'll make it a little bit more complicated in the next chapter. Let's see, for instance, problem number 2. So this is problem number 2. This is a little bit more difficult, and it will make more sense when we go to chapter 4 and we actually introduce all the forces, because we're using naming here, nomenclature, and introducing forces that we still may not know, although it's pretty trivial anyways. But we're going to solve it together now and see exactly what we're trying to do here. It says that there is, compute the least acceleration with which a woman of 45 kilograms can slide down a rope if the rope can withstand a tension of only 300 newtons. So we can write that the maximum tension is 300, that's information, and that the mass of the woman is 45 kilograms. And then we can just make a diagram. Let's say there's a rope hanging and the woman is just here, hanging from the rope, right? And what's going on in here, right? That's the balance of forces. So what we do is, as usual, a free body diagram. This will become more important when we have more forces later. But basically, if we just take the woman, we replace the woman with a point. That we can do because we remember the point particle. Now it's going to be we can call it mass particle as well before. And then we're going to observe is that we're going to have what? What forces are acting on this woman? Well, there is a force of the woman, which is her own weight. If she drops the cord, if she drops the rope, she's going to just fall down, right? Like any object, just drop it in earth, she falls down. So we know that there is a force pointing down that we will introduce chapter 4, that's the weight, and that's actually, if we put the arrow pointing down, we can even say this is m times g, right? It's negative, well, let's keep it negative, just remember it always points down. And is there any other force? Well, if there's no other force, the woman falls down, and it falls down with g. That's free fall. there needs to be another force because there's a string and that is a rope, and that's actually the force of the rope is what we call the tension. So we can have a force of a tension that is pointing upwards, right? And so I'm asking, what's the net force? Well, the net force is going to be the sum of all the forces. What are the forces acting in here, right? And I will be 1, 2, 3, 4, 5. This will be force 1, this force 2, etc. Right? Doesn't matter. Basically, we add the forces. So what is the resultant force or the net force? That's going to be the tension minus m times g. And how much is that? That's mass times the acceleration of the woman. Right? So we can rewrite the entire thing. Let's make it, for instance, here, force of tension minus m times g. It's equal to m times the force times the acceleration. And now the question is, what's the least acceleration? And that's confusing because you were expecting what's the maximum. But here's the thing. Let's replace with the numbers, maybe to see that easier. Mass is 45, g we can take to be 10. The mass is 45, the acceleration we don't know. Actually, we're being asked about the acceleration, right? The minimum acceleration. It seems weird because we have been told maximum tension and we might have been expecting, oh, what's the maximum acceleration so it doesn't break. But we'll see why it's the least in a second. And then we can just see from here that the force of tension, actually, this is minus 450, and this is 45 times A, which means that the force of tension is going to be 450 plus 45.8, right? This is minus goes there. And now you might just say, right, what acceleration can this value be? We know that the tension, the rope breaks as soon as you have 300 newtons. This is 300 newtons. And if it's 300 newtons, if 450 plus 45 times A is 300 newtons, the rope breaks. So let's analyze different values, just inspection. You don't do this in the problem, but just so we understand. If acceleration is, let's say, 1 meter per square second, okay? Basically, we're saying the woman is accelerating very slowly, but upwards. What would happen? 45 times 1 is equals 45. 450 plus 45, the tension would be how much? 495. 495 is larger than 300, which is the force of tension max, right? So what would happen in that scenario? The rope would break. So we cannot have a 1 acceleration. We need to make it smaller. Plus 0, so 450 newtons, and this is larger than 300. So the rope breaks, this breaks, and that breaks, right? Then we see what's going on. This number is always going to be larger than 300. So what we're trying to make is that 450 plus 45 times A needs to be smaller or equal to 300, because otherwise this, that is the force of tension, will be larger than the maximum and it will break. How do we make this 450 smaller than 300? Is only if we subtract, and we subtract only when acceleration is negative. And how much negative is actually we're gonna try to solve for, and that's why it says the least, the minimum least. What does it say? The least acceleration, right? We're trying to find the minimum, the smallest acceleration, minimum. Otherwise, it will break. So because if if A is minus 1,000, obviously works, or minus 1 million, it works. I just want to try to get the smallest acceleration, but negative acceleration, such as that goes to 300. And so, of course, that's going to be 450 plus 45A is smaller than 300, which means that 45A is smaller than 150 negative, which means that A needs to be smaller than 150 divided by 45, and that's going to be 15, that's going to be minus 10 divided by 3, which is going to be minus 3.3, something like that, meters per square second, right? So we're going to find that the acceleration needs to be smaller than 3.3 meters per second. So how does the woman avoid the rope to break? If she goes downwards with an acceleration at least negative 3.3. So going downwards at least with 3.3 meters per square second. Every second she goes down, she needs to gain 3.3 meters per second in velocity. So that's why we see the tension otherwise would be too much and it would break. So that's going to be also important, because if we ask the woman, can the woman stand there and just relax and chill a little bit while hanging? No, she cannot. But amazingly, if the woman keeps going down and gaining velocity, then she never applies the tension above the maximum tension of the rope, and then she will not break the rope and fall to her demise, we could say, right? So problems 4, 5, and 6 in discussions are actually a nice illustration of how we combine dynamics and kinematics to build the entire description of the motion. In chapter 4, we're saying that it's asking us how much force we need to apply on a car that it weighs 1,500 kilograms to make it go from 100 kilometers per hour. And if we convert this to meters per second, that's going to be 28 meters per second. That's the initial velocity, to a final velocity of 0 meters per second. And then it's asking us how much force is required to do this over a distance of 55 meters. So let's build it. Instead of having all this information, let's keep using our nice kinematic things, and we're going to have that the x final position, remember the delta x is x minus x0, so if we take this to be 0, why not? Then x becomes just directly 55. So I can just identify 55, then here I just take 0, then the initial x, the final velocity x is going to be 0, the initial velocity is going to be 27.8 meters per second, the acceleration and the time. So I don't have information about time, and I'm trying to find the acceleration. How do I know that? Because I'm being asked about the force. And again, this is like a reverse engineering thing. This is a detective quest. I may either find time or acceleration. Which one is the one I'm trying to find? Well, remember that the question is the force. And how do I find out the force? Well, I know that the force is mass times acceleration. It's in one dimension, so we don't even need to use vectors, right? So do I have the mass? Yes. Do I have the acceleration? No. So actually, this is what I want to find. So what is being asked? Force. Force is equal, do I know force? No. How can I know it? If I have the mass and I have the acceleration. Do I have the mass? I do. Do I have the acceleration? I don't. I need to find the acceleration. And then you come back down here and say kinematics. I have final position, initial position, final velocity, initial velocity, acceleration. This is what I'm trying to find, and I have no information about time. What equation do you use here? Well, you use the classic equation of v squared is equal to v squared 0 plus 2a delta x. No time information. So what's the final velocity? The final velocity is 0. What's the initial velocity? 27.8 squared plus 2 times acceleration delta x, and delta x is 55. So we can just write directly 55. So what's the acceleration? That's going to be minus 27.8 squared divided by 110, and that's the acceleration. Now one thing that you're going to see, one thing you're going to see, of course, is that this acceleration is negative, and actually the value of the acceleration is minus 7 meters per second, square second, excuse me, right? And so we know the acceleration. Why is the acceleration negative? Because we're going from velocity to 0 velocity. So we're having a car that it was just going with a certain velocity, and at the end, it has no velocity. So what do I need? I need to have an acceleration that points the opposite direction. I need a force that acts this way, and that force, of course, is going to be the braking force. Of course, it's going to be the braking force. It's going to produce a deceleration or a negative acceleration as expected. And then, of course, the question is how much is the force? So the force, again, is mass times acceleration. So how much is the mass? 1,500. How much is the acceleration? Minus 7. So how much is going to be that? That's 0, 0. That's a 3, and it's a 10. So, and there's a negative number. So that's going to be minus 10.5 10 to the 3 newtons, or 10,000 minus 10,500, or we also can say minus 10.5 kilo newtons, where kilo, remember, is 1,000. If I have a kilometer, 1,000 meters. If I have a kilogram, 1,000 grams. If I have a kilonewton, 1,000 newtons. So easy. We see how do we start from a situation where we can get all the information in our problem, and we ask how much is the force required to get to this situation. This is the force. For instance, if you knew that your car has a force for the brakes, a maximum force of 20,000 newtons, Would you be able to stop in these conditions? Yes, in 55 meters you would be able to stop. But what if your car had a braking system that it's only 7,000 or 5,000 newtons? Well, then you wouldn't be able to stop, you would crash. That's why it's also important to know if the distance was longer, then you wouldn't have that problem. Maybe, depends on how much longer. But that's basically the idea here. We're going to have situations where we're seeing forces, and we can figure out the forces, based on changes or observations of the motion. And sometimes we're given forces, the initial interaction, and figure out what's the motion. But both directions work the same way. From force, we get acceleration. From acceleration, changing velocity. From changing velocity, position. Or from position, changing position, we get velocities. Changes in velocity, we get accelerations. From accelerations and mass, we get the force. It doesn't matter, both ways work, and this is how we see we come together in explaining why did the car come to stop. Before we were able to express or explain how the car came to stop with this acceleration. That was the end. But now we're saying why. Well, why? Because you have a force acting opposite to the motion of 10,500 kilonewtons, 10,500 newtons. So let's see problem number 6. So in problem number 6, we said that there is a force acting on a 5 kilogram object that reduces its velocity from initial velocity of 7 meters per second to a final velocity of 3 meters per second in time 3 seconds. What is the force? And again, what is the force? Well, to find the force, we need the mass times acceleration. Do we know the mass? Yes. Do we know the acceleration? No. So actually the question is, what's acceleration? How do we find acceleration? Let's write our equations. X sub 0, v sub 0, a, and t. A, we don't know. T, 3 seconds. Initial velocity 7. Final velocity 3. Do we have any information on position? We don't. We're missing position, right? We're missing spatial position. So what do we do when we're missing spatial position? We need to use an equation that doesn't use spatial position. So basically v is equal to v sub 0 plus a times t. How much is v? V is going to be 7. V sub 0 is going to be 3. The other way. So that's going to be 3. And that's going to be 7. Right? V is 3. V sub 0 is 7. Plus acceleration, we don't know that, times 3. So we can see that goes there subtracting. So it's going to be minus 4. It's equal to a times 3. A is going to be minus 4 divided by 3, which is 1.333, blah, blah, blah. Right? And negative. So what's the acceleration? The acceleration then, we can write it here. The acceleration then is minus 1.3 period, right? So minus 1.3. What is the force? Well, force is just minus 1. It's going to be mass times acceleration. So it's going to be 5 kilograms times minus 1.3. So how much is that force? About 6.5, 6.66 or something like that, right? But 6.5 negative newtons. Units of force is newtons. And remember, because mass acceleration, that's kilograms. Acceleration is meters per square second. So newtons is just kilograms per meter per square second. So force in newtons. So that's why it's important we were saying to work in international system, because you could use these formulas using kilometers per hour, but that would not be newtons. You would have to take kilometers per hour, convert into meters per second, and then that will give you newtons, right? So 6.5 newtons and negative. Why is negative? Because we go from an initial velocity to a lower velocity. What are we doing? We are decelerating. We're braking. We need a force opposed to motion. Now let's say in this same problem, let's say that the object didn't change its velocity. If the object didn't change its velocity, v minus v sub 0 would have been 0 because they're both the same, so acceleration would have been 0, and the force would have been 0. So again, you will see, if there is no force, there is no acceleration, there is no change in the state of motion, or we can say if there is a change in the state of motion, that is, if there is a change in velocity, then we can define the acceleration, which is how fast that change in velocity happens. And then we know, and why is that change in velocity happening? Because we have a force. Or we can say whenever there is an interaction, it's going to produce whenever there is an interaction, net force, right, is going to produce an acceleration. That's going to tell me how fast the change in motion is going to happen, and so I'm going to have a non-zero change in the state of motion. Principle of inertia tells you that if this is 0, if force is equal to 0, right? Mass times acceleration is 0, and because of the mass is non-zero, then acceleration is 0. And if acceleration is 0 and time is non-zero, 0 is change of velocity over time, and so the change in velocity is 0. So velocity final minus initial is 0, means that final velocity is the same as initial velocity, right? There is no change in the state of motion. That this number could be 0, meaning it's stationary, or it could be 1,000 kilometers per hour, or a million, or a trillion, or whatever you want. It doesn't matter. What matters is the velocity is constant. So again, very important. Change is a presence of forces, net forces, acting on the object, changes the state of motion. But that doesn't mean that the object was stationary. It might have been stationary, and after it becomes moving, or it might have been moving, and then it becomes stationary, or it might have been moving and changed towards different velocity. But in any case, if there is no force, the state of motion, which is another way of saying the velocity, remains constant. So problem number 8 is just a realization about the same as problem number 3, that the forces are vectorial. It's not the same to push the sofa towards TV than far away from the TV, as we saw during the lectures. So calculate the sum of two forces exerted on the boat by workers A and B. So we're going to have an object, and there's going to be a force, 40 newtons, with 45 degrees, and there's going to be another force, 30 newtons, and 37 degrees. Now, if the object, let's say, was stationary, what's going to happen is that the object is going to start moving. For sure, it's going to be moving horizontally. We will be extremely surprised if the boat started to move in the opposite direction. If the object was moving in the opposite direction, then we would know that there is a force more than this one and this one, because when we add them together, the force is going to be positive. This object being here and moving to the opposite way an instant later means the velocity is going in that way. So unless there is a constant velocity, because they cancel, which obviously they don't, it means that I need to have a balancing force. So this is the kind of thing you can start thinking as soon as you solve problems. And now, of course, excuse me, the question is going to be in which direction. Now you might be tempted to say, well, this is 40 newtons and this is 30, so it's going to go up. But they're acting at a different angle. So what I need to do actually is decompose the forces, and this is always the case, we said it before. So let's use this force here. So we're going to have, we can call this force 1, I think these are called A and B actually. So we can just say that the force A is just equal to what? 4ax and 4ay. And what are these? Well, so katoa. What is this one? This is a sub y. So this is what? Opposite. So that's going to be so sine. And what is this one? This is x, and that's what? K. So k. So it's going to be the cosine. So then I'm going to say that is going to be f sub a cosine of 45, f sub a sine of 45. Both are the same. And f sub a, of course, the modulus of f sub a is going to be 40 newtons. So if we calculate those numbers, that's going to be, 28.3 newtons, 28.3. You can just write the units outside of the vector. So that's the first force. What about the second force? Well, force B is going to be what? Well, it's going to be, of course, B sub x and force B sub y. What's B sub x? B sub x is this one. So what is that one? The adjacent of the 37 degree. So that's going to be 30 newtons times cosine of 37. And what about the y? The y is what? The opposite, right? So that's sine. So that's going to be 30 times sine of 37. Very important. Again, math is describing a physical situation. Does it make sense that my force, that my force is vertical? No, the force is not vertical. It's positive. It's negative, the vertical component. So I need to add a minus here, or I would have it wrong, right? Two ways of getting that minus: if you define this 37 as minus 37, otherwise add it just positive and then correct it manually. Okay, and if we solve for these numbers, of course, we're going to find that this is 24 minus 18.1 newtons. So what's the total force? We can say the net force. That's going to be the sum of all the forces, which is, of course, force of A plus force of B, these being vectors. And so how much is that? Well, that's going to be 28.3. 28.3 plus 24 and minus 18.1, right? And then if we add them together, that's going to be 28.3 plus 24, which is going to be 52.3, and 28.3 minus 18.1, which is going to be 10.2, and positive, right? It's 10 minus, is positive. And so that's going to be the total force acting on the object. Now, how much is its magnitude and how much is its strength? So the force, the net force, we can do here. The net force, of course, is going to be the square root of the sum of those. So it's going to be 52.3 squared plus 10.2 squared. And if you make that and the square root, you find that this is 53.2 newtons. And if you calculate the angle, now I can add these vectors. And adding these vectors will be the same as I take this one over here and I put it here and I just make the resultant. Or I just take this one in here, and because I didn't write them at the scale and the angle doesn't make a lot of sense. But then we're going to see that that has 52x component. So we're going to go, let's say 52. And then we're going to be, let's say this is 52. And then it's going to be 10.2. So 10.2. So it's going to be something like this net force, right? That's going to be the net force. So we see that graphically. So of course the angle here is going to tell us that, which we can just do that, which is y over x. So tangent of theta, it's equal to y over x. And so theta, you solve for the tangent, and theta is equal to 0.195, excuse me, 11.11 degrees, basically. Correct, so 11 degrees. So the idea here, we see 11 degrees. If this force had been less strong, or if this had been stronger, then we might have found a situation where the vector resultant will be pointing down. And so this number would have been negative. Again, you could just have put everything positive, find the angle, and remember the angle is still going to be pointing downwards. So at the negative, if it had been negative, you could always have added 360, and then it would go all the way to the negative anyways, starting from the positive, right? Direction is the inclination over the horizontal axis, so I just need to move 11, and I need to go with a strength of 53.2 newtons. Vectors are forces, watch out for that. Take the vectors, add them all together as vectors, distribute into horizontal and vertical components, and put them in the kinematics for the horizontal acceleration and the vertical component of the acceleration. The fact that this force was like this, or the force was, we could have said, basically the horizontal component of the forces determine only the acceleration in the horizontal. The vertical components only determine the acceleration in the vertical. If this vector had been like this, instead of like that, just like, let's say like this, right? This vector has the same horizontal component, so the horizontal component of the force would have been exactly the same. And therefore the acceleration in the horizontal component would have been the same. We would have changed the acceleration in the y component, of course. So this is again the idea. Let's distribute vectors that are in 2 dimensions to horizontal and vertical, and then we can solve them as 1-dimensional very easily.